Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 3, Material and Energy Balances, and we are beginning now to look at steady flow processes and the energy balances necessary on those. We had the general form of the energy balance, also known as the first law, shown here as the energy accumulated is equal to the energy that flows in minus the energy that flows out, plus the work and heat transfer with the surroundings. When we defined enthalpy, we were able to combine U and PV, so that simplified the energy in and out of the system. So the flow terms have enthalpy plus the kinetic and potential energy, and the accumulation term has just internal energy. Otherwise, this is the same expression as we had before. We want to begin looking at steady flow processes because, frankly, in chemical engineering, most of our processes operate at very close to steady state. We'll at least make the assumption that they are. There will be minor changes, but for the most part, they operate at steady state for design purposes. So what this means is that at any point in the control volume, remember CV from Chapter 1 is control volume, so at any location in this space, the state of the mass does not change with time. So if I were looking at a point on an impeller of a pump, for instance, all the time, every time I was looking there, it would always have the same state. So the pressure, the temperature, etc., all exactly the same. The mass flow rates and states of the flow streams will not change with time. That's important because if the flow rate coming in varies, then suddenly it isn't truly at steady state. And that the rates of work and heat transfer are constant. Again, no change over time. If I do this, then we have our material balance becomes just the sum of all of my mass in is equal to the sum of all of my mass out. You cannot have accumulation if it's at steady state. Now, our energy balance, what this has told me up above is that I'm going to have flow in and out, but I am going to not have any change within the space. And that tells me that the work of expansion and contraction needs to be zero. Okay, I'll still have shaft work, that rotation, right? But I'm not going to have any expansion or contraction because that changes the state inside the control volume with time. If I do that, then what I end up with is the simplified version of the energy balance. There's no accumulation. This is equal to the sum of all of the flowing energy in minus the sum of all of the flowing energy out plus the shaft work and the rate of heat transfer. This is going to be our general steady state energy balance. We can write this a little bit, the zero equals is awkward, right? So we can write this so that it isn't quite so awkward by saying that Q plus W is the sum of what comes out minus what comes in. So that's an important distinction. I am now saying out minus in is the Q plus W that comes and goes from the system. And this work is the shaft work. Let's look at an example. We're going to be looking at a pump. In this case, water is being pumped from a sump tank. So a sump tank is like a tank down below the ground, and I have a pump up at the top of this tank. It's going into a storage vessel, and the delta Z is going to be 10 meters. Water is going to be flowing at 3 kilograms per second. the inlet pressure is 50 bars. The inlet temperature is 100 degrees C. The exiting pressure is 250 bars. And the exiting temperature is 100 degrees C. Now it says, assuming the pump is adiabatic, okay, adiabatic we defined in chapter 1, and that is that Q equals 0. That's what adiabatic means. Remember, we may also call that well insulated, another euphemism they use. And based on this, we want to find the power input. Power is the rate of work. And so that's what we're looking for is W dot. The first thing we're going to need is we're going to need a simplified version of the first law, and we are going to need data. So take a moment and see if you can get this problem started. So put a stop on the video, work on this for a little while, and come back and join me. The form of the first law, or the energy balance for our steady flow system, is this, but the first thing I'm going to point out is that I don't need the summation signs because there's only one stream coming in and out. Okay? Also, they told us that Q is equal to 0 because it was adiabatic. Now, velocities. Did they say anything about kinetic energy? They mentioned a height difference, but not anything about kinetic energy. So therefore, we will assume that delta KE is equal to 0. No good reason for that, but we don't have any information about it. And it is typical that the velocity in and the velocity out are very close to being the same. If you do a material balance, and if you have the same size pipe at the inlet and the outlet, it has to be the same. Now, what about the z's? They did mention that delta z is equal to 10 meters. If I define the bottom to be z equal to 0, then the top would be 10 meters. And so I can get rid of this piece because it is equal to my 10 there, right? The simplified version of this equation is that the power is equal to the mass flow rate, in and out will be the same, times the change in enthalpy plus GZE. I have ZE, G I know is 9.8 meters per second squared. Mass flow rate was given as 3 kilograms per second, but I don't know the enthalpies. So we need to go to the data tables for those. So go on back to the appendix of your textbook and see what you come up with for HE and HI. Pause the video. In this case, these materials are compressed liquids. When you looked in the saturated table, the value of the temperature was colder than the saturation temperature, and so therefore these are compressed liquids in both cases. We can look, therefore, in the compressed liquid tables, which is up after the superheated vapor table, but it's organized in the same way. And we find that H at the inlet is 422.8 kilojoules per kilogram, and H at the exit is 438.0 kilojoules per kilogram. Now, we're going to plug these into our simplified first law, but again, pay careful attention to the units. So pause the video and see what you come up with and come back and compare answers. So the mass flow rate is 3 kilograms per second. The enthalpy difference is 438 minus 422.8 plus 9.8 times 10. Now the units are where we get in trouble. Kilojoules per kilogram is being added to meters squared per second squared. So we need a unit conversion. This is one that is not ever directly in a conversion factor table, but it's a really useful one. I would recommend that you write this down somewhere. 1 kilojoule per kilogram is 1,000 meters squared per second squared. Now you can get to that doing it kind of, step by step using traditional unit conversions. But this is really helpful because it's going to get me out of the meters squared per second squared and into kilojoules per kilogram. More frequently, I end up using it the other direction, but it doesn't matter. That's a useful conversion factor. When I do that, I end up with that the power to run this pump is 56.7 kilowatts. That concludes this example, and it concludes this lesson. We are going to be looking at examples for different steady flow processes in subsequent videos. Thank you very much for your time.